It was late in 1998. The world was worrying about the Y2K bug, but a small group of astronomers was worried about the entire universe. There are two teams, actually. One was the Supernova Cosmology Project led by Saul Perlmutter. The other was the High Z Supernova Search Team with Brian Schmidt and Adam Ries. They were rivals. Both were using the world's best telescopes, including the Hubble, to look at distant exploding stars, type Ia supernovae to be specific. These stars are cosmic standard candles. They all explode with roughly the same brightness. So if you see one that looks dim, you know it's far away. If it's very dim, it's very far away. The plan was simple. Measure the distance of these supernovae and measure their redshift, how much their light has been stretched by the expansion of the universe. This would tell them how fast the universe was expanding in the past. Everyone knew the answer they were supposed to find. The universe is full of matter. Matter has gravity. Gravity pulls things together. So the expansion of the universe should be slowing down. The only question was by how much. Maybe it would slow down and eventually collapse in a big crunch, or maybe it would slow down forever but never quite stop. But that's not what they found. The data was clear, and it was wrong. The distant supernovae, the ones that show us the past, were dimmer than they should have been. They were farther away than the expansion models predicted. This meant that in the billions of years it took their light to reach us, the universe had expanded more than expected. It hadn't slowed down. It had sped up. The announcement was a shock. Perlmutter's team presented their findings in January 1998. The rival team confirmed it a month later. The expansion of the universe is accelerating. Something is pushing everything apart. They called this something dark energy. This discovery wasn't just a new piece of the puzzle. It was a terrifying new puzzle altogether. It meant the future of the universe was not a gentle slowdown or a fiery crunch. It was cold, dark isolation. Every galaxy not gravitationally bound to our own will eventually be pushed away from us so fast that its light will never reach us. They will disappear beyond a cosmic horizon one by one. The sky will empty, the universe will end in a big freeze, a state of maximum entropy where nothing happens. Forever, this discovery also cemented an old idea. There is an edge to what we can see. Not a wall, but a horizon, a boundary in space-time, the observable universe. It's the sphere around us containing everything whose light has had time to reach Earth since the Big Bang, about 13.8 billion years ago. The actual edge of that sphere is now about 46.5 billion light years away because the space itself has been expanding. We can't see beyond that. We will never see beyond that. And that accelerating expansion is pushing that edge away from us faster than the speed of light. So we are left to wonder, what's out there? What secrets, what horrors, what wonders are hiding just beyond the edge? Number 16, our physics is just a local by law. The speed of light is 299,792,458 meters per second. In a vacuum, the charge of an electron is a specific negative value. The strength of gravity is what it is. If the strong nuclear force were just 2% stronger, protons would not be stable, and atoms as we know them could not exist. If it were 5% weaker, we would only have hydrogen, no other elements. We call these the fundamental constants of nature. They are the rules, the source code of reality. We assume they are the same everywhere. The same yesterday, today, and forever. The same here as they are in the Andromeda Galaxy. The same here as they are at the edge of the observable universe, but what if they aren't? What if the rules of physics that we have so carefully discovered are just a set of local bylaws applicable only to our cosmic neighborhood? Beyond the horizon, things could be fundamentally different. This isn't just wild speculation. It's a potential solution to one of the biggest problems in physics, the fine-tuning problem. The problem is that many of these fundamental constants seem to be tuned to an impossibly precise degree to allow for the existence of life. Well, if you change them even slightly, the universe becomes a sterile, uninteresting place. Stars don't form, or they burn out in a million years. Chemistry becomes impossible. The universe might have flown apart in the first second of its existence, or collapsed back into a singularity. Why is our universe so perfect for us? One explanation is the anthropic principle. It states that we observe the universe to be this way because if it were any other way, we wouldn't be here to observe it. This sounds like a circular argument, but it becomes a powerful scientific idea if there are other universes. Or, more simply, other regions of our own universe far beyond what we can see. The theory of eternal inflation proposed by physicists like Alan Guth and Andre Linde suggests that our Big Bang was not a one-time event. Instead, it was just one bubble of space-time that nucleated and expanded within a much larger, eternally inflating multiverse. In this larger reality, Big Bangs are happening all the time. Each bubble can cool down and settle into a state with its own set of physical laws, its own fundamental constants. It's like boiling water. Our universe is one bubble in a vast, roiling pot. So just beyond our cosmic horizon, we might not just find more galaxies. We might find the boundary wall of our bubble, and on the other side of that wall would be another universe. A place where the strong force is a little stronger, or gravity is a little weaker, or the speed of light is different. Most of these universes would be stillborn, dead on arrival. They might be empty voids of radiation, or crushed into black holes, or a bizarre plasma of particles we can't even imagine. In such a universe, an atom might be the size of a planet. Light might behave like a liquid. Time might have 2 dimensions instead of 1. These regions would be so alien that our physics would be useless to describe them. And we couldn't even call it physics in the same way. Like, it would be a different operating system for reality. The thought is humbling. All our science, from Newton to Einstein to quantum mechanics, could be nothing more than a description of a local anomaly. A lucky accident in an infinitely vast and varied cosmos where most of the territory is governed by rules we could never comprehend. The edge of the observable universe in this view is not just a limit of our sight. It is the border of our understanding, the point where our laws cease to apply. Number 15, the universe is a lower dimensional surface in a higher dimensional space. A sheet of paper is two-dimensional. A creature living on it, a flatlander, would know only length and width. It would have no concept of up or down. If you, a three-dimensional being, were to poke your finger through the paper, the flatlander would not see a finger. It would see a circle the cross-section of your fingertip appear out of nowhere, perhaps change its size, and then disappear. It would seem like a miracle, a violation of their physics. The pressure of a gas is the result of countless atoms hitting the walls of their container. It is a macroscopic property that emerges from microscopic behavior. The laws of thermodynamics, which govern heat and energy, are statistical laws that work on large scales. They do not apply to a single atom. What if our universe is like that sheet of paper? Right. What if our three spatial dimensions and one time dimension are just a brain short for membrane floating in a higher dimensional space called the bulk? This is a central idea in M theory, a candidate for the theory of everything that unifies all the forces of nature. In M theory, the universe could have up to 11 dimensions. We are just stuck on a four-dimensional 3-space plus one-time surface within it. This isn't just a mathematical trick. It could explain some deep mysteries. For example, why is gravity so much weaker than the other forces, like electromagnetism? It's about 10 raised to the power of 40 times weaker. This is the hierarchy problem. The brain world scenario offers an answer. Perhaps the other forces are confined to our brain, but gravity is not. Gravity can leak out into the extra dimensions of the bulk. This would dilute its strength, making it appear weak to us, the creatures stuck on the brain. So what lies beyond the edge of our observable universe? According to this idea, it might not be more space in our sense. It could be the beginning of the bulk. The edge could be where our brain curves or ends or interacts with another brain. We might be heading towards a collision with another universe brain. Such a collision, some theorists propose, could be what triggered our Big Bang. The Great Rift Valley in Africa is a place where two tectonic plates are pulling apart, but it is still part of the larger three-dimensional Earth. Similarly, the edge of our observable universe might be just a feature on our brain, with the vastness of the bulk lying just off the map in a direction we can't point to. This higher dimensional reality could be all around us, not just beyond the horizon. The extra dimensions predicted by M-theory are thought to be compactified or curled up into tiny, complex shapes called Calabi-Yau manifolds at every point in our space. Too small for us to see, but perhaps far away these dimensions are not curled up. They could be large. A journey to the edge of the universe might be a journey to a place where space itself has more dimensions. A place where you could step off our universe the way you can step off a path. What would that be like? It's impossible to visualize. It would be a reality with more directions to move in, governed by the full, terrifying complexity of 11-dimensional physics. Our universe would seem like a shadow, a projection of a deeper reality. Number 14, time is running backwards. The arrow of time seems fundamental. Things are born, they age, they die. Eggs break, they don't unbreak. And we remember the past, not the future. This directionality is tied to the second law of thermodynamics. It states that entropy, a measure of disorder, always increases in a closed system. The universe started in a very low entropy state at the Big Bang, highly ordered, and has been getting more disordered ever since. This is the arrow of time. But the fundamental laws of physics themselves don't have a preferred direction of time. A video of two billiard balls colliding looks perfectly normal if you play it forwards or backwards. The underlying equations are time symmetric, so why is the universe so different? Why the one-way street from past to future? A controversial but fascinating idea proposed by physicists like Julian Barber suggests that the Big Bang might not have been a beginning. Instead, it was a point of minimum entropy, a moment of perfect order in the middle of a much larger, timeless reality. From this central point, time flows in two opposite directions. Think of it like a fountain. Your water shoots up from the center and then flows down both sides. The Big Bang is the center. On one side, you have our universe, where entropy is increasing and time flows forward as we experience it. But on the other side, there is another universe, a mirror universe. It is also expanding away from that central Big Bang point. But from our perspective, its entropy is decreasing. Its arrow of time is pointing in the opposite direction. What would this mean for what lies beyond our cosmic horizon? It would mean that if you could somehow cross that boundary and keep going, you would eventually reach a point where time, relative to you, starts to flow backward. You would see stars unforming, galaxies pulling together, and planets assembling from dust and gas. You would be moving toward their Big Bang, which is also your Big Bang. To the inhabitants of that universe, if any could exist, everything would seem perfectly normal. They would experience their time flowing forward from their past to their future. They would see our universe as the one where time is running backward, the two arrows of time are relative. There is no absolute forward. This two futures model is an attempt to explain the low entropy of the Big Bang without resorting to special pleading. It didn't start that way. It's just a turning point, a place of maximum order from which two universes branch out. The model relies on the nature of gravity. Gravity tends to clump things together. Barbour and his colleagues argue that for any system of particles governed by gravity, there will be a unique moment of maximum density and order. The system will expand and become more complex and disordered in both directions of time away from that point. So beyond the edge, there might not just be more space, there might be a different temporality. A universe that is an exact mirror of ours, not in terms of what it contains, but in the direction of its becoming. It's a staggering thought. The end of our universe, the heat death of maximum entropy, would, from the other side, look like the beginning. and our beginning would look like their end. The two universes are forever separated, back to back in time, born from the same instant. Number 13, the universe is a single, enormous quantum object. A single electron can be in multiple places at once. This is called superposition. It only chooses a definite location when it is measured or observed. This is a core principle of quantum mechanics. For the last century, we have treated quantum mechanics as the law of the very small atoms, particles, and general relativity as the law of the very large planets, galaxies, the universe. But what if the universe itself is a quantum object? The many worlds interpretation, MWI, of quantum mechanics, first proposed by Hugh Everett III in 1957, takes this idea to its logical conclusion. Everett suggested that every time a quantum measurement is made, the universe splits. In one universe, the electron is here. In another parallel universe, the electron is there. There is no collapse of the superposition. All possible outcomes happen, each in its own separate world. This branching happens constantly, creating a near infinite number of parallel universes. These universes are not far away in space. They are all around us, coexisting in the same space-time, but in a different state of reality, inaccessible to each other. They are different branches of the universal wave function. What does this have to do with the edge of the observable universe? In the standard MWI, these worlds are separate, but some physicists speculate that the separation might not be perfect over immense cosmic distances. The edge of our observable universe is defined by the speed of light. It is a horizon of information, but quantum mechanics has a strange property called entanglement. Two entangled particles can be linked in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance. If the entire universe was born from a single quantum event, the Big Bang, then perhaps everything in it is, on some level, entangled. The particles on the far side of our horizon could be entangled with the particles here. And perhaps on that vast scale, the clean separation between our universe branch and other branches of the MWI begins to break down. Beyond the horizon, we might not find a simple continuation of our reality. We might find a region where the quantum wave function of the universe has not decohered into a single classical reality. A place where galaxies are in a superposition of being in multiple locations at once. Where the laws of cause and effect are blurred. A raw, uncollapsed quantum foam. This idea is linked to the concept of the cosmological wave function, an attempt to describe the entire universe with a single quantum equation, the Wheeler-DeWitt equation. This equation has no time variable. It describes a static, timeless block of all possible universes. Our perception of a single, evolving universe would be just one path through this vast quantum landscape. So, beyond the edge, we might find the other us's. The other versions of our galaxy, our solar system, and ourselves that split off at some past quantum event. We wouldn't be able to interact with them in a normal way. It would be more like finding the raw code of reality, the underlying superposition from which our classical world emerges. It would be a place where all possibilities are still physically real and coexisting. A true quantum realm, but on a cosmic scale. Number 12, we are living inside a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. It has a boundary called the event horizon. Once you cross it, you can't get back out. The observable universe also has a boundary, a cosmic horizon. We can't see anything beyond it. And due to accelerating expansion, galaxies crossing that horizon are, in a sense, lost to us forever. The math describing these two types of horizons is surprisingly similar. This has led some physicists, like Nikodem Poplawski, to propose a radical idea. What if our entire universe exists inside the event horizon of a black hole? The theory goes like this. When a massive star collapses, it forms a singularity, a point of infinite density. General relativity predicts this, but the theory breaks down at that point. Quantum mechanics should take over. Instead of a singularity, some theories suggest the matter rebounds in a big bounce. But what if this bounce creates a new expanding universe? In this model called cosmology with torsion, the intense gravitational forces and spinning of the collapsing matter create a huge repulsive force that prevents a singularity from forming. Instead, it creates a baby universe on the other side of the event horizon. This baby universe is spatially isolated from the parent universe it was born in. From the outside, it still just looks like a black hole, but from the inside, it's a new expanding cosmos just like ours. This would mean that every black hole in our universe could be a gateway to another universe. And our own universe would be the product of a black hole that formed in some other older, larger parent universe. What lies beyond the edge of our observable universe? The rest of the black hole we are in. Our Big Bang would not have been the beginning of everything, but simply the moment of the bounce inside the black hole. The matter that formed our universe would be the matter from the star that collapsed in the parent universe. This idea solves several problems. It explains where the energy for the Big Bang came from. It provides a reason for the arrow of time. Time flows away from the bounce, and it might even explain dark energy. The spin of the parent black hole could impart a rotational force to our universe, which we perceive as an accelerating expansion. So, if we could travel to the edge of our observable universe and beyond, we would not find an infinite expanse. We would find a boundary, not a wall, but the event horizon of the black hole that contains us. What's on the other side? A parent universe, a place with its own stars and galaxies. And in that universe, we would be just one of countless black holes, invisible and inaccessible from their perspective. This theory, sometimes called the black hole genesis or cosmological natural selection model, also suggests a kind of cosmic evolution. Black holes that produce baby universes with physical constants conducive to making more black holes will have more offspring. Our universe, which is very good at making black holes, might be the result of this cosmic scale natural selection. It is a universe fine-tuned not for life, but for reproduction. The fact that it is also fine-tuned for life might just be a side effect. Number 11, the universe is a computer simulation. The resolution of a digital photo is limited by the number of pixels. If you zoom in too far, you see the individual squares. The speed of a video game character is limited by the processing power of the computer running it. And there is a fundamental clock speed, and our universe also seems to have fundamental limits. There is a minimum possible length, the Planck length, about 1.6 x 10 raised to the power of 35 meters. There is a maximum possible speed, the speed of light. Could these be signs that we are living in a simulation? This is the simulation hypothesis popularized by philosopher Nick Bostrom. The argument is simple. If any civilization ever reaches a point where it can create ancestor simulations of their past reality that are indistinguishable from the real thing, they will likely run many such simulations. If they run billions of them, then the number of simulated consciousnesses would vastly outnumber the number of real ones in the base reality. Therefore, it is statistically more probable that we are one of the simulated beings rather than one of the real ones. This idea moves from philosophy to physics when we ask how we could test it. If the universe is a simulation, it must be running on some kind of computer. That computer would have finite resources. The simulation would have to be built on a discrete grid, a lattice of points in space-time, like the pixels on a screen. Physicists like Silas Bean have suggested that we might be able to detect this underlying grid. For example, high-energy cosmic rays should behave differently depending on the direction they travel if space is a lattice. So far, no such effect has been found, but the grid could be far too fine for us to detect. So, what could be hiding just beyond the edge of the observable universe, the edge of the simulation? The hard drive limit. The observable universe is vast, but it's not infinite. A simulation would only need to render the parts of the universe that the simulated beings us can observe. There would be no need to compute the state of galaxies that are beyond our cosmic horizons. It would be a waste of processing power. It's like a video game that only renders the part of the world the player is currently in. The landscape beyond the fog of war doesn't exist until you go there. But for us, we can't go there. The edge of the observable universe is a perfect boundary. Perhaps it's not a natural boundary. Perhaps it is a computational shortcut. Beyond it, there is simply nothing, or more accurately, unallocated memory. Null pointers. The simulation simply doesn't render that part of the map because it knows we can never receive information from it. The accelerating expansion of the universe could even be a feature of the simulation. Maybe the simulation was getting too complex, requiring too much processing power as galaxies interacted. Pushing everything apart simplifies the calculations needed. It's a way for the system to manage its resources. In this scenario, there is nothing out there. The universe we see is all there is. The edge is a true edge, not a physical wall, but the end of the program. It's a deeply unsettling idea. It means our reality is not fundamental, it is a created artifact, and like any program, it could have a program, and it could be turned off. Number 10, the universe repeats itself in a never-ending cycle. The universe began in a hot, dense state, the Big Bang. It is currently expanding and cooling. The standard model predicts it will end in a cold, dark, empty state, the Big Freeze, be the end. But what if that's not the end? What if it's the beginning of the next cycle? This is the central idea of conformal cyclic cosmology, CCC, a model proposed by the renowned physicist Sir Roger Penrose. Penrose finds the extremely low entropy state of the Big Bang to be a deeply troubling mystery. Why did it start so perfectly ordered? His solution is radical. The Big Bang was the continuation of a previous universe's end. Here is how it works. In the far, far future, after all the stars have burned out, after all the black holes have evaporated through Hawking radiation, a process that will take an unimaginably long time, like 10 raised to the power of 100 years for a supermassive black hole, the universe will be nothing but a cold, thin soup of photons, neutrinos, and other stray particles. There will be almost no mass. At this point, the universe will have lost all sense of scale. Without mass, there is no way to measure size or time. A tiny universe full of high-energy photons is physically indistinguishable from a huge, empty universe full of low-energy photons. The physics is conformal, meaning it looks the same at all scales. According to Penrose, at this end state, the universe forgets how big it is. Mathematically, the infinitely large future can be smoothly joined, or mapped, onto the infinitely small, hot, dense state of a new Big Bang. The end of one aeon becomes the beginning of the next. So what is beyond the edge of our observable universe? The remnants of the previous aeon. Penrose argues that this transition would not be perfectly smooth. Some information might leak through. Specifically, he predicts that collisions between supermassive black holes in the previous aeon would have released enormous gravitational waves. These spherical waves would have expanded and, at the end of that eon, would have been imprinted on the new Big Bang as slight temperature variations. He calls these Hawking points. He and his collaborators claim to have found evidence of these points in the cosmic microwave background CMB, the afterglow of our own Big Bang. They appear as small, circular regions of slightly higher or lower temperature. The claims are highly controversial and are not widely accepted by the physics community. Most cosmologists believe these patterns are just random fluctuations, but if Penrose is right, it would be a revolution. It would mean we have already seen evidence of a time before our universe. It would mean the universe is eternal, not with a single beginning, but with an endless cycle of births and deaths. In this view, the space beyond our horizon contains the echoes of a former cosmos. The universe is vastly older than we think. Our 13.8 billion years is just one chapter in an infinite book. The structure we see, the distribution of galaxies and voids, might have been seeded by events that happened in the universe that existed before ours. We are living in the ashes of a former reality, a reality whose ultimate fate is to become the fuel for the next. Number 9. There is an infinite expanse of true nothingness. We say that space is empty, but it's not. Even the darkest void between galaxies is filled with things. There are stray atoms, there is radiation like the cosmic microwave background. Most importantly, there is quantum foam. According to quantum field theory, empty space is a bubbling, seething cauldron of virtual particles that pop into and out of existence for fleeting moments. Space itself has energy, the vacuum energy, which is what we think dark energy is. But what if, beyond the edge of all this, there is true nothingness? Not a quantum vacuum, but an absolute void. No space, no time, no fields, no particles, no laws of physics, just non-existence. This idea is different from the universe just ending at a boundary. It suggests that our universe, this bubble of space-time and energy, is an isolated anomaly. A temporary, localized event in an eternal, infinite background of non-being. Philosophically, this is the ultimate something from nothing problem. Why is there a universe at all? Physicists like Lawrence Krauss have argued that nothing in the quantum sense is unstable and will naturally produce something like a universe. But this relies on the pre-existence of quantum laws. What if there are no laws? This scenario paints a lonely picture of our cosmos. Imagine our universe as a single campfire in an infinite, dark, cold desert. The fire is the Big Bang. The light from the fire is the observable universe. The area beyond the light is just more desert. But eventually, the desert ends. And beyond that is not more land, but the absence of anything. In this model, the edge of the observable universe is just a line of sight. But far beyond that, there would be a true edge. The edge of space-time itself. What would it be like to approach it? It's impossible to say. Our laws of physics would break down. As you got closer, perhaps the vacuum energy would drop to zero. The virtual particles would stop appearing. Space-time itself might become less stiff, more fragile, until it simply dissolved. This idea is hard to support with any theory, because theories are descriptions of something. It is the ultimate outside context problem, but it resonates with a deep intuition. The universe seems extravagant, all these galaxies, all this energy. Maybe it's not the norm. Maybe the default state of reality is nothing, and our universe is a spectacular and ultimately temporary exception to the rule. So beyond the horizon, there would be more galaxies, more clusters, more voids, but eventually the pattern would thin out. The expansion of the universe would not just be creating more space. It would be encroaching on the nothingness. Our universe would be a bubble of is expanding into an ocean of is not. This raises a terrifying question. If the universe is expanding into nothing, could the nothing leak in? Could the properties of true nothingness, the absence of physical law, begin to infect the edge of our space-time? This is pure speculation, of course, but it highlights the profound difference between the nothing of a quantum vacuum and the absolute nothing of philosophical thought. One is a dynamic and creative medium, the other is the end of all possibilities. Number 8, the universe is a fractal. A fractal is a pattern that repeats itself at every scale. If you look at the coastline of Britain from space, you see a complex, jagged shape. If you zoom in on a single bay, you see a similar jagged shape. If you zoom in on a single rock, its outline is also jagged and complex. The pattern, or at least its statistical properties, is self-similar. What if the universe is a fractal? From our vantage point, we see a cosmic web of galaxy clusters, filaments, and voids. This is the largest scale of structure we can observe. The universe looks clumpy. The standard cosmological model, however, assumes that on scales larger than a few 100 million light-years, the universe becomes smooth and uniform. This is the cosmological principle. It is a foundational assumption of all our models. But what if it's wrong? What if the clumpiness continues all the way up? What if the cosmic web we see is just one thread in a much larger cosmic web? And that larger web is a thread in an even larger one, and so on forever. This is the idea of a fractal universe. In the 1980s and 90s, some astronomers like Luciano Pietranero argued that the distribution of galaxies did in fact look like a fractal as far as our surveys could see. They suggested that the assumption of homogeneity was just a convenient simplification, not a proven fact. Most cosmologists today believe the evidence strongly supports homogeneity on large scales. The cosmic microwave background, for instance, is incredibly smooth, with temperature variations of only 1 part in 100,000. But the debate is not completely settled. Some recent large-scale galaxy surveys have found structures like the Sloan Great Wall or the Hercules Corona Borealis Great Wall that are larger than what the standard model would easily predict. These might be statistical flukes, or they might be hints that the universe is lumpier than we think. If the universe is a fractal, then what lies beyond our horizon is simply more of the same structure, but on a grander scale. Our entire observable universe might be just one particle in a much larger cosmic structure. This structure would have its own superclusters and supervoids on a scale we can't imagine. This would have profound consequences. General relativity, as currently applied to cosmology, relies on the assumption of a smooth average density. If the universe is a fractal, the average density is never reached. The equations would have to be completely rethought. Our understanding of the universe's expansion and evolution could be wrong. For example, the accelerating expansion we attribute to dark energy might just be a local effect. It could be caused by us being in a relatively empty part, a void of a much larger fractal structure. The gravitational pull from the denser parts of the fractal, which are outside our horizon, could be pulling us, creating the illusion of a mysterious repulsive force. In a fractal universe, there is no edge, in the traditional sense, just an endless hierarchy of structure. It would be a universe of infinite complexity. It would also be a universe without a true average, a universe that would look different depending on the scale you use to observe it. The ultimate question would be what created the initial fractal pattern, and does the pattern continue inward to scales smaller than subatomic particles, as well as outward? Number 7, we are in a region of unusually low density. The cosmological principle states that the universe is homogeneous and isotropic on large scales. This means it looks the same in all directions and from all locations. It is the foundation of modern cosmology. But it is an assumption. We can only verify it within our observable patch of the universe. What if it's not true? What if we happen to live in a special place? Specifically, what if we live in a giant cosmic void? Not an empty void, but a region of space that is significantly less dense than the cosmic average. This is the Hubble bubble, or KTZ void hypothesis. The idea is that our galaxy and a large chunk of the surrounding universe, perhaps billions of light years across, is situated in an underdense bubble. Outside this bubble, the universe is denser. This difference in density would affect our measurements of cosmic expansion. Here's why. We measure the expansion of the universe using supernovae as standard candles. We measure their distance and their redshift. We then infer the expansion rate, the Hubble constant. But if we are in a void, things get complicated. The denser regions outside the void would exert a stronger gravitational pull on the galaxies inside the void. This would make the local expansion rate inside the bubble faster than the true global expansion rate of the universe as a whole. This could explain the mystery of dark energy. When we look at very distant supernovae which are outside our local void, they would appear to be accelerating away from us even more slowly than we'd expect from our local, faster expansion rate. This would create the illusion of an accelerating expansion over time. The acceleration would not be caused by a mysterious repulsive energy filling all of space. It would simply be a local gravitational effect. We are being pulled by the mass outside our bubble. If this is true, then What lies beyond the edge of the observable universe is a normal universe. A denser, more typical region of the cosmos. We are the anomaly, our little corner of the universe is an exception. This idea is not mainstream. To explain the supernova data completely, the void would have to be very large and very empty, which is statistically unlikely according to the standard model. Also, there are other lines of evidence for dark energy, like the cosmic microwave background and baryon acoustic oscillations, which a simple void model has trouble explaining. However, it is a scientifically testable idea. If we are in a void, we should see subtle effects on the cosmic microwave background and on the distribution of galaxies. Some studies have claimed to find evidence for such a void, while others have refuted it. The jury is still out. But it's a powerful thought. It would mean that one of the biggest discoveries in modern science, dark energy, is actually a mistake. A misinterpretation of the data caused by our unusual location. It would be the ultimate cosmic provincialism. We thought we had discovered a new fundamental property of the universe, but we were just living in the cosmic equivalent of the suburbs and misjudging the hustle and bustle of the city that lay just over the horizon. Number 6, the universe was born from the collision of higher dimensional brains. In M theory, our universe is a three-dimensional brain existing in a higher dimensional space, the bulk. What if there are other brains, parallel universes floating just a short distance away from us in that extra dimension? The ekpyrotic model proposed by Paul Steinhardt, Neil Turok, and others takes this idea and uses it to replace the Big Bang theory. Ekpyrosis is a Greek word for a cosmic fire, a conflagration. In this model, the Big Bang was not a beginning from a singularity, but a violent collision. The model envisions at least two parallel brains. For eons, they are cold, empty, and nearly parallel. But there is a force between them, a manifestation of gravity in the higher dimension that slowly pulls them together. Eventually, they collide. The collision is not at a single point, but all over the infinite surface of the brains. The kinetic energy of this cosmic clap is converted into the matter and radiation of a new, hot, dense universe. This is what we call the Big Bang. After the collision, the brains bounce off each other and begin to move apart again. As they separate, our universe, which is on one of the brains, expands and cools. Stars and galaxies form, but the cycle is not over. The brains will eventually slow down, stop, and begin moving toward each other again, destined for another collision trillions of years in the future. This cyclic model has some advantages. It avoids the singularity of the Big Bang, a point where physics breaks down. It also provides a natural explanation for the smoothness and flatness of the universe without needing cosmic inflation, a period of hyper-fast expansion just after the Big Bang, which is part of the standard model but lacks a firm theoretical foundation. The brains were already smooth and parallel before they collided, so what lies beyond the edge of our observable universe? More of our brain universe, for one, but more profoundly, just next door in the fourth spatial dimension is another universe, the one we collided with. Right now, it could be just a millimeter away. We can't see it or touch it because we and all the forces except gravity are stuck to our own brain. But its gravitational influence could be felt. Some have speculated that dark matter, the mysterious invisible substance that makes up most of the matter in the universe, could be ordinary matter on the parallel brain, whose gravity we can feel across the gap. This model paints a very different picture of our cosmos. It's not a one-off event. It is one cycle in an eternal dance between two worlds. The space beyond our horizon is not the most interesting beyond. The most interesting beyond is in another direction entirely, a direction our senses are blind to, the universe next door, and one day we are destined to meet it again in a collision that will end our universe and create the next. Number 5, the universe is just one option out of an infinite menu. The landscape of string theory is perhaps the most bewildering and controversial idea in modern physics. String theory is a leading candidate for a theory of everything. It posits that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. The different vibrations of these strings give rise to all the different particles we see. For the theory to be mathematically consistent, it requires the existence of extra spatial dimensions, usually 6 of them. These extra dimensions are compactified or curled up into complex shapes. The geometry of these shapes, these Calabi-Yau manifolds, determines the properties of the universe. It sets the values of the fundamental constants like the charge of the electron and the strength of gravity. It determines which particles exist. The problem is the theory doesn't predict one unique shape for these extra dimensions. It allows for a colossal number of different possibilities. The estimates vary, but a commonly cited number is 10 raised to the power of 500. That's a 1 followed by 500 zeros. Each of these possibilities corresponds to a different vacuum state, a different way the universe could be. Each would have its own unique set of physical laws. This collection of all possible universes is the string theory landscape. Philly place, but a landscape of possibilities. However, the theory of eternal inflation provides a way to make this landscape physical. As the multiverse expands, different regions can tunnel into one of these 10 raised to the power of 500 vacuum states. Each time this happens, a new bubble universe is born, with its own set of physical laws determined by its specific Calabi-Yau manifold. Our universe is just one of these bubbles, one choice from an almost infinite menu of options. So, what is beyond the edge of our observable universe? The rest of our bubble. And beyond that, the eternally inflating space of the multiverse. And dotted throughout that space are other bubble universes, an infinite number of them. Most of these universes would be utterly hostile to life. They would have the wrong number of dimensions or forces that are too strong or too weak. But with 10 raised to the power of 500 options, it's not surprising that at least one, ours, would have the right properties for stars, planets, and people to exist. This is another appeal to the anthropic principle. This idea is deeply unsatisfying to many physicists. It means that we can never predict the fundamental constants of nature from first principles. The best we can do is say that we live in a universe that is compatible with our own existence. And physics becomes an environmental science where we are just measuring the local conditions of our particular cosmic bubble. If you could travel beyond the horizon, you would eventually reach the edge of our bubble. You would see the wall where our laws of physics break down, and on the other side would be the roiling, expanding space-time of the multiverse. And in the distance, you might see other bubbles. Some might be similar to ours. Others might be made of pure light or strange forms of matter governed by forces we can't imagine. It would be the ultimate confirmation that our reality is not special, but just one of a near infinite number of cosmic experiments. Number 4, an identical copy of you is out there. The observable universe is finite. It's a sphere about 93 billion light years in diameter. But the universe as a whole could be infinite. The evidence we have from the flatness of space points in this direction. If the universe is infinite, and if the distribution of matter is roughly uniform on the largest scales, then a startling conclusion becomes inevitable. Everything that can happen must happen. And it must happen an infinite number of times. Here is the logic. Quantum mechanics tells us that in any given patch of space, there are a finite number of possible ways particles can be arranged. A finite number is still an unimaginably huge number, but it's not infinite. You can calculate this number. It's about 10 raised to the power of 10 raised to the power of 118. This is the number of possible quantum states that can exist in a volume the size of our observable universe, a Hubble volume. If the universe is infinite, then there are an infinite number of these Hubble volumes out there. An infinite number of patches of space, each the same size as our own observable universe. Now, you have an infinite number of Hubble volumes, but only a finite, though, huge number of ways to arrange the particles within them. It's like having an infinite number of Scrabble sets, but only a finite alphabet. Sooner or later, you are going to spell the same word again. The patterns must repeat. This means that somewhere out there, far beyond our cosmic horizon, there is another Hubble volume that is identical to ours. A region of space where the arrangement of particles is exactly the same. There is another planet Earth. With another person who is exactly you, reading this exact sentence, and it doesn't stop there. In an infinite universe, there are an infinite number of these identical copies. There are also copies that are almost identical, but with one tiny difference. A universe where you decided to have tea instead of coffee this morning. And a universe where you are left-handed instead of right-handed. A universe where one single atom in your fingertip is in a different quantum state. Every possible variation exists. This is the concept of the cosmological patchwork, or level 1 multiverse, as described by physicist Max Tegmark. It's not a different universe in a different dimension, it's just a region of our own, single, infinite universe that is so far away we can never see it. How far away would you have to travel to find your nearest twin? The estimates are staggering. The distance to a Hubble volume with an identical history to ours would be roughly 10 raised to the power of 10, raised to the power of 118 meters. This number is so large that writing it out would be impossible. The number of atoms in our universe is a trivial 10 raised to the power of 80 by comparison. So, while your cosmic twin is almost certainly out there, you will never meet them. The space between you is expanding far too fast, but it is a sobering thought. Your life, your choices, your uniqueness might just be one random pattern in an infinite cosmic tapestry. A pattern that is repeated over and over across an unimaginably vast expanse. What lies beyond the horizon is not strange new physics. It's just more of the same. You know, so much more that it includes another you. Number 3, the universe is not expanding. The redshift of distant galaxies is one of the pillars of modern cosmology. We observe that the light from distant galaxies is shifted to longer, redder wavelengths. The standard explanation is the Doppler effect, caused by the expansion of space itself. The galaxies are moving away from us, stretching the light waves as they travel. This is the foundation of the Big Bang model. But what if this interpretation is wrong? For decades, a small but persistent group of scientists has championed an alternative, the tired light hypothesis. First proposed by Fritz Zwicky in 1929, the same man who first inferred the existence of dark matter, this idea suggests that the universe is not expanding. It is static. The redshift we see is not caused by galaxies moving away. Instead, it is caused by photons of light losing energy as they travel across the vast cosmic distances. The longer the journey, the more energy they lose, and the redder they appear. The light simply gets tired on its trip. If this were true, it would completely upend cosmology. There would be no Big Bang. No expanding universe. The universe could be infinitely old and infinitely large in a steady state. So what lies beyond the edge of our observable universe? Just more galaxies stretching on forever in a static space. The edge would only be an edge of visibility, the point at which the light from galaxies has become too tired, too redshifted for us to detect. It would not be a fundamental boundary in time, as the Big Bang model suggests. The tired light hypothesis has been largely rejected by the scientific community for several reasons. It has trouble explaining key observations. For example, observations of distant supernovae show that their explosions appear to last longer. This is perfectly explained by time dilation in an expanding universe. The clocks in the moving galaxies are running slower from our perspective, but it is very difficult to explain with tired light. A tired light model would redden the light, but it wouldn't stretch the duration of the event. Furthermore, the cosmic microwave background CMB is a huge problem for tired light. In the Big Bang model, the CMB is the leftover heat from the hot early universe. A static universe has no natural way to produce such a perfect uniform black body radiation spectrum coming from all directions. Despite these problems, some researchers continue to explore modified versions of the idea. They argue that a mechanism for light to lose energy without being scattered, which would blur the images of distant galaxies, an effect we don't see, might exist. If they were right, it would be the biggest scientific revolution in a century. It would mean that the universe is not an evolving, dynamic place born from a fiery explosion. It is a vast, quiet, eternal entity. The drama of the Big Bang and cosmic evolution would be an illusion, a misreading of the evidence. The space beyond our sight would hold no secrets of our origin, just an endless, unchanging sea of galaxies. Number 2, the cold spot is a bruise from another universe. The cosmic microwave background CMB is a snapshot of the universe when it was just 380,000 years old. It is remarkably uniform, the same temperature, about 2.7 Kelvin in all directions. But it has tiny fluctuations, hot and cold spots that represent the seeds of all future structure like galaxies. These fluctuations are random and should be evenly distributed, but they are not. There is one spot in the southern sky in the direction of the constellation Eridanus that is abnormally large and cold. It is called the CMB cold spot. It was discovered by NASA's WME satellite in 2004 and confirmed by the Planck satellite. It is about 70 microkelvins colder than the average, and it is huge, spanning about 1.8 billion light years. The probability of such a spot appearing by pure chance in the standard model of cosmology is low, maybe 1 in 50. So what is it? One possibility is that it's a statistical fluke. In any random dataset, you will get unlikely patterns. Another, more conventional explanation is that it is caused by a massive supervoid between us and the CMB. A large region with very few galaxies would have a lower gravitational pull, causing photons from the CMB passing through it to lose a bit of energy, making them appear colder. There is some evidence for such a void, but it is not clear if it is large or empty enough to explain the entire effect. But there is a third, much more exotic explanation. The cold spot could be a bruise, a scar on our universe from a collision with another bubble universe in the distant past. This idea comes from the eternal inflation multiverse model. If our universe is one bubble among many, it's possible for these bubbles to collide. Laura Mersini-Houghton, a physicist at the University of North Carolina, has developed a theory predicting that such a collision would leave a detectable mark. The collision would have happened very early in our universe's history, before the CMB was formed. So it would have pushed energy out of a large region of space, creating a scar that would later manifest as a cold spot in the CMB. The theory also predicts another, smaller void on the opposite side of the sky, but the evidence for that is weaker. If true, this would be the first concrete observational evidence of a multiverse. It would mean that beyond the edge of our observable universe, there are other entire universes. And at least one of them is close enough to have bumped into us. What would that other universe be like? It would have its own physical laws, its own constants of nature. The collision would have been a cataclysmic event, but it happened so early that it just left this subtle temperature fluctuation. This is a highly speculative idea, and most cosmologists are skeptical. They favor the supervoid explanation or a statistical fluke. But it is a testable idea. Future, more detailed maps of the CMB and galaxy distribution could either rule it out or provide more supporting evidence. For now, the cold spot remains a mystery, a nagging anomaly in our otherwise very successful model of the universe. It could be nothing, or it could be a window, a tangible piece of evidence that what lies beyond our universe is not just more of the same, but something else entirely, another reality, another set of laws, another universe. that once long ago reached out and touched our own? Number one, just more universe forever. The simplest answer is often the most likely, and the simplest answer to the question of what lies beyond the edge of the observable universe is more universe. More of the same, more galaxies, more clusters, more filaments, more voids, stretching on and on, either to infinity or in a vast but finite loop. This is the baseline assumption of modern cosmology, the cosmological principle. The idea that our patch of the universe is not special, that the universe is on the grandest scales uniform and the same everywhere. So the part we can't see is probably just like the part we can. This might sound boring compared to colliding brains or mirror universes, but the implications of this simple idea are anything but boring. The sheer scale is difficult to comprehend. Our observable universe contains an estimated 2 trillion galaxies. If the universe beyond is the same, then that number is just a tiny fraction of the whole. If the universe is truly infinite, as the data on its flat geometry suggests, then the number of galaxies is infinite. The number of stars is infinite. The number of planets is infinite. And as we saw, the number of times every possible arrangement of particles occurs is also infinite. This is a profound and humbling concept. It means that there is no center, there is no edge. Our edge of the observable universe is not a real physical boundary. It is just our horizon. An alien in a galaxy 10 billion light years away has its own observable universe, its own horizon. Its sphere of vision overlaps with ours, but it can see parts of the universe that we cannot. And we can see parts that it cannot. Everyone has their own bubble of sight, but all the bubbles exist within the same single vast cosmos. This simple, powerful idea is the most supported by the evidence we currently have. The universe appears to be flat, which implies it is infinite. The distribution of galaxies appears to become uniform on the largest scales we can measure. The cosmic microwave background is incredibly smooth. Everything points to the idea that what you see is what you get, and that there's a whole lot more of it that you can't see. So, beyond the edge, there is another galaxy, much like our own. And beyond that, another, and another. There are star systems with planets that are eerily similar to ours. There are life forms that might have evolved in similar ways. There are civilizations that might be asking the same questions. And there are vast stretches of cold, empty space. All the wonder, all the terror, all the beauty, and all the mundane emptiness of our own observable universe is replicated over and over across an expanse so large that the word large loses all meaning. This is perhaps the most awe-inspiring possibility of all, not because it is strange, but because it is not. It means the universe is not a bizarre zoo of different physical laws and dimensions. It is just a place, a single, consistent, staggeringly enormous place. The great mystery is not what lies beyond the horizon. The great mystery is why there is so much of it, and in all that vastness, we are here on one small planet in one ordinary galaxy, looking out and wondering.